All right, we're back. We are going to be doing Calc AB Notes 23, which is all about slope fields. We're going to work on page 4, but I wanted to look at the end of page 3. The last video about page 3 is just like incredibly long, so I wanted to kind of cut it off. So something to really keep in mind is when you are looking at a slope field, you're looking at all the possible solution curves. So we're looking at possible solution curves or the particular solutions. What you are not looking at is you are not looking at, so let's highlight that in like some extreme color. You are not looking at the graph of the differential equation. So for example, if dy dx equaled 2x, the graph of dy dx would just be the line 2x, like, and you would recognize it right away, right? And it would change from negative to positive at 0 and all that good stuff. When you're looking at a slope field, you're looking at all the possible solutions to dy dx equals 2x. So we could actually figure that out, right? The solutions are x squared plus c. The slope field will look like all these little tangent segments, and if you back up enough and look at it, you're like, oh, I can see a lot of parabolas there. So you're not looking, when you're looking at a slope field, not looking at the graph of the differential equation, you're looking at all of the possible particular solutions. And it's hard to get your head around that, and I don't know that people necessarily actually do confuse them, but I wanted to really clarify that. So let's see if we can use that idea to kind of work backwards. So in these, we actually have the slope field, which means we have a sense of what the solution curves look like. So what I'm going to do is I'm going to draw a couple. So for this, for example, this first one, let's see, you just kind of like follow. Then I'm going to go like this, and then I guess like this, and then maybe like this. So you do your best, right? And then we can go back this way. You can see it's kind of like 0-ish there. Maybe that's way too short. Like I know that because I actually know what this one is. Like this. And then I think I'm probably also not going high enough on this. This is just how hard, even when I know what it's a slope field for, I pretty much can't do it. So this, but then that's just one of the potential solution curves, right? We could also go like this, and then maybe like this, and then like this. And, you know, you just kind of like do what you do. Let me pick up some speed here. I'll draw, oh God, what do you, don't autocorrect. Oh no, it's all going to heck. There, oh, what is, okay. So I don't really know what's happening here. It's decided that it would autocorrect my, my curve into a line or something. I'll do one more. That's what I was about to say when like, you know, the stuff happened. Okay, quick curve. You know, you just follow the contours as best you can. So the question is, what do all of these look like? These look like, to me, they look like trig functions. It actually looks to me like just sine, right? So for the first one that I drew, you start out at an intercept, and then you go to a maximum, intercept, minimum, intercept. I think that's just sine. So I think the solution curves look sort of generally like y equals sine of x, and then maybe plus c. I mean, definitely plus c, but like you really only need it for one because the derivative of c is going to be 0. So if that's what dy dx looks like, then the differential equation will look like the derivative of that. So for this particular slope field, dy dx would look like cosine of x. So if you were given dy dx equals cosine of x, and you were asked to make a slope field for it, this picture would be the slope field. So we would end up with this. And then when we draw our solution curves in the slope field, they're going to look like sine of x. This is the idea. So here, all right, let's draw a couple. So I tend to start with the ones that like the x-axis is involved with. Like there's no really compelling reason to do that. I think this, and then I think this. I think that could be one of the solution curves. I think also we could move down like this, like this. I don't know if you've watched my videos and I've tried to draw a quadratic in any of them, you know that I think it's impossible to draw quadratics well. they just grow so fast, like faster than you think. All right, so it seems to me like these all have some things in common. All the solutions appear to be decreasing until you get to x equals 1, increasing after x equals 1. So that's a thing. Therefore, they all seem to have a minimum at x equals 1. So I think that maybe, I don't know exactly what it looks like, but I think that the solutions look like the quantity x minus 1 squared and then plus c. I think all of my solutions look like that. They all have their vertex on x equals 1, and then you can move it up and down. So if that's the case, then I would expect the differential equation to look like 2 times the quantity x minus 1. So now what I don't know is I don't know if they actually look like 1.1 times the quantity x minus 1 squared. Like, there's almost no way to know that from a differential, from a slope field rather. But this gives me a very good idea of what differential equation I should be looking for if it turns out this is like a multiple choice question, which frequently these are. So that's what we're talking about here, is we're trying to like just get used to this concept. So here, this is a very weird looking slope field. So for example, I think actually, I think I can, let's take advantage of the ability to make a line. So I think that could be a solution. I think that could be a solution. I think that all of these, I think we're just getting linear solutions, which maybe there. So I think that the solutions to this all just kind of look like, what would I say the slope is though? I would say, I mean, I think that if I start at 0, I think the slope is probably 2. I think these look like y equals 2x plus c. But there's really no way for me to know. I mean, 1, 1, it's like if I go through the point 1, 1 and follow the slope, I do not think I go through 0, 0. I don't know that I necessarily go through 0, negative 1, but like whatever. You do your best. Like, I think that this is what it looks like. And so I would expect a differential equation that looks something like that. So I'd be on the lookout at the very least for a differential equation that's dy dx is equal to some positive constant. I think greater than 1, but who really knows? That's kind of the best you can do. Okay, so this one's going to be more challenging. This one I actually think, well, let's see. So say I wanted this point, right? So I'm going to go back and kind of like this, and then we're going to go this way. And then I think I'm going to end up off the slope field. I think like here, it looks like everything will have a minimum when x is equal to 1. It looks like everything will have a maximum when x is equal to negative 2. I'm going to use that idea. I'm actually going to, so like maybe this, I don't know, that could do it. So it's like a Bob Ross moment when you're drawing your solution curves, where you're like, happy little solution curves. They just kind of gently go up, hit their maximum, and come back down, moving through the flow. And then you go up like this, and whatever. Okay, I'm not going to do more than 2 of them because that's taken forever. I don't really know what to say about this particular one. So what I'm going to do is I'm going to say I think that I know what the differential equation looks like. And I think that because I think that everywhere that x is negative 2, we're going to get a maximum. And then everywhere x is 1, we're going to get a minimum. So I actually think I can write the differential equation for this, or at least very close to the differential equation. So I think the differential equation is going to definitely have a factor of x plus 2, because if there's a factor of x plus 2, then when x is equal to negative 2, the slope will be 0. And I want that to happen because that's always happening. I also think there's going to be a factor of x minus 1 for like exactly the same reason. Now, I also know, so really the question is, do I want this or do I want a negative number in front of it? You know, do I want a coefficient? So if I think about it, as it's currently constructed, -2, we'd have 1. That would be a quadratic, like the differential equation represents a quadratic that opens up. So I'm gonna go, this is for dy dx. It's gonna go plus, minuses, and then pluses. Look at the slope field, and you can see that the solutions are increasing until you get to -2, decreasing after, and then increasing after 1. So I think that this could be our differential equation. If I think this could be our differential equation, which I do, so there's no way to, I'm gonna just write like start here on this one, because if you're somehow skipping around in the video and you just got here, we start here and we're gonna use this to find what our solution curves look like. So I think that I'm saying dy dx is equal to, what is this? X squared plus x minus 2 minus 2. So I think the solution curves look something like 1/3 x cubed plus 1/2 x squared minus 2x plus c. I think they look something like that. But again, I don't know. Maybe it's 1.1 times x plus 2x minus 1. There's no way to really know, right? You're just trying to get a general sense for it. And if you look at these, you get a very general sense of what these things should look like. So in particular, it's useful to know where slopes are equal to 0, increasing, decreasing. Just have that family of curves in your mind, right? Like I recognize quadratics. I would recognize sine, cosine, negative cosine, linear functions, obviously. And then sometimes when they get more complicated, like this, these all look like cubics, right? So I would expect for this last graph, I would expect the solutions to look like cubics. So I would expect the differential equation to be quadratic. And that's fine if that's like the level of detail you're looking for. But because you have so much information, you can actually go backwards. You can try to write the differential equation and from that come up with your cubic, which is like a big deal. It's really good to be able to do that. So let's see what the bottom box here says. It's just kind of a summary. So, and it's got nothing really to do with this page, just like things you always need to be thinking about. If dy dx is just, what? You're not a highlighter at all. What color? Here we go. If dy dx is a function of x, then y doesn't impact the slope. So along vertical lines, you get the same slope. That's an idea that we're going to hammer in a lot. If dy dx is just a function of y, x doesn't impact the slope. So if you move left and right, nothing's going to happen. So the slopes along horizontal lines are always going to be the same. So that's just, we're just bouncing back to stuff from a previous page. So that's it for this page. I'm going to come back in the next page, do some more stuff with slope fields, and I will see you there.